Welcome to our AIFS Ensemble webinar. This AIFS Ensemble is a completely new model, and in a couple of minutes my colleague Simon Lang will explain all about it. But first I will give a few housekeeping remarks. So this webinar is being recorded, and we will upload the recording on the implementation page and on our YouTube playlist with all the model updates. You can ask questions using Q&A primarily, but if Q&A for some reason is not working for you, you can also ask in chat, and our colleagues will try to answer while during the presentation. And if some questions are unanswered, after the presentation, we will also try to answer them. So today, Simon Lang will present the model. Maartje Kuilman from User Services will present the data practicalities for our users. But before them, our Director of Forecasts, Florian Pappenberger, will give us a few introductory words. Florian, on to you.
I'm going to make this very short. This is a very proud moment for us. It has been the work of many for a long time. I'm here also welcoming you on behalf of our Director General, Florence Barbier, who unfortunately couldn't be here with this morning. But I think it's great that we got to this moment that we are actually operationalizing an ensemble of the machine learning model. I hope you're going to enjoy the presentation by Simon as much as I will enjoy it. And please don't hold back with any questions. And as I always say in these presentations, the most important for us is your feedback. We need your feedback to improve the model. We need your feedback to improve our services. We need your feedback to create better outputs and better products so they're useful for you. And with that, I think I just hand over to Simon to start.
Thank you very much, Florian. Yes, today we are here to talk about our new AIFS Ensemble system. And to start and to give a bit of background, of course, the backbone of our forecasting system for many years and still is the integrated forecasting system, our NWPE physics-based system. And just to recap how it works, we start with the data assimilation step, where we fuse a short-range forecast from the IFS with the latest observations. And these are combined, and this generates the initial conditions of our system. And then in the IFS, we start from these initial conditions our physics-based model and then generate an ensemble of predictions. So 50+1 forecasts. And what we want to talk about today is now to basically the new AIFS forecast chain. AIFS is our machine learned forecasting model. And basically this part, we stay with the data simulation of our physics-based model. The initial conditions come from the IFS, but then the whole forecasting step now also exists in the machine learning world. So this is handled also now by our AIFS forecasting system. So it creates now, starting from the physics-based initial conditions, an ensemble of 50+1 forecasts. And this basically complements now our AIFS forecasting chain. So far, we had our AIFS single model, which became operational in February this year, which produces one forecast, one deterministic forecast. And now this is complemented, or we also introduced now the IFS ensemble, which produces then, of course, 50+1 members, so a range of forecasts. And these are machine learned. This is a machine learned weather forecasting model. So what does this mean? Here in the NWP, or in the physics-based model, what we do is we write down basically the physical laws that govern the evolution of the atmosphere in form of computer code, and this is then run and this produces the forecast. While in the machine learned weather forecasting model, the model learns from our ERA 5 reanalysis how the atmosphere evolves, and then we also let it learn from our operational high resolution analysis. So It really just learns from the forecast fields how the atmosphere evolves. And this is done in the following way. Basically, we show it 40 years of Era 5 reanalysis data and then 10 years of operational data. And the model learns to forecast always 6 hours into the future. So from one analysis, we step to the next 6 hour, as we step forward 6 hours in time to the next analysis, and so on and so on. And the model, by this, the model learns how to really evolve the atmospheric state. And then in forecasting mode, what we do is then we basically forecast 6 hours into the future, and then the model is initialized by this forecast again to the next 6 hours and so on. So we forecast auto-regressively into the future. And basically like an NWP model, but we have a much larger time step, a 6 hour time step here. So to explain how the model is set up or how it works, again, a recap from also from the AIFS single. Basically, we have an encoder, processor, decoder design. The model sees inputs. These are the atmospheric state at time t and 6 hours before that, time minus 6, t minus 6 hours. So these are presented to the models. These are our initial conditions from the AIFS, basically. And then it is fed into the model. The encoder maps it into an internal lower resolution representation, but higher dimensional. And then the decoder maps it. The processor runs 16 times, and then the decoder maps it back to the output grid, and that's our prediction at 6 hours into the future. And the whole system is trained in several steps. So there's the first step where we have the pre-training phase, where we really where the system just learns to map 6 hours into the future. And then there are additional steps. So step 2 is that the model learns to auto-regressively forecast up to 72 hours ahead. So it really produces, or it learns how to produce good forecasts 72 hours, 3 days into the future. And then we also, step 3, which is not on here, is like a fine-tuning phase where we fine-tune the model on the operational high-resolution analysis. And this gives us the model. Just to talk about the processor a bit, it's a transformer, which probably all of you have heard about at some point now, like in the large language models like ChatGPT and so on. So once we have mapped the data to its internal AIFS internal grid, a transformer then attends to all the grid points, and that's how information is aggregated from grid points far away to the target grid point. And because we have a sliding window, so it only sees, each grid point only sees a part of the globe, but because we run it 16 times, it can actually aggregate information from far away. So that's schematically here in gray, while the attention window itself is relatively confined over many processor layers. Information can then travel. And of course, that's the setup of the AIFS single as well. And now the question is, what is new here? How do we actually train the ensemble? And this is via a proper score loss. So basically what we do is, instead of training a single forecast, well, basically training a single forecast model, we train here an ensemble via an ensemble approach. So we give the model initial conditions, and yeah, I should say it's the same forecast model, but we train a small ensemble of forecasts. So basically, we give it a number of initial conditions. In our case, it's just a deterministic analysis, and then this is mapped to the hidden state, and each ensemble member we use during training gets then a representation of noise, which is injected in the processor. And then it has to produce a forecast state. Once these are there, we gather them and we compare them with the target state, the truth, and via our CRPS loss. So that's popular score also for verifying ensemble forecast. You've certainly heard about it. And basically what this does is it encourages the model to have a low error, but at the same time, the members should have the right variability that matches its error. And yeah, as I said, it's the same model, but each member sees a different representation of noise. So by design, it has to produce interchangeable ensemble members. So what do we gain from that, you can ask? So here is again a representation. So as I said, we use the CRPS-based loss. In practice, we use a variant of the CRPS, which is called the fair CRPS, which accounts for corrects for the number of ensemble members we use. So we can actually train AIFS CRPS, the AIFS ensemble with 2 members only. And because the fair score has some degeneracy, we also introduce a almost fair CRPS, but that's just a detail. And one outcome of this is that we get members which have a realistic level of variability. And what do I mean by that? So if we look here at the forecast from AIFS single, so that's a 1-day forecast and that's a 10-day forecast here, then what we can see is that while initially there's still quite a lot of small scale detail, at day 10 we can see this smoothing we have seen in many machine learning models now. So where you basically lose a lot of small scale detail. You still have your clinic systems and everything, but you lose it. It is this smoothing effect that all looks a bit blurred out. And of course, in mean squared error training or deterministic training, the model learns to basically lose features where it would otherwise incur the double penalty for. So it reduces the activity of the model. And when we compare this now to the AIFS ensemble system, because we use the CRPS loss, this is not really possible for the model. So at 1 day, you see lots of small scale features. And then indeed at day 10, you see the same level of small scale features. So the model has not lost any of this small scale variability, but it really has to preserve it to fulfill its training target. And this, of course, then makes for much more realistic looking forecasts. So I think the physical realism of the fields is improved a lot. Oops. I lost the forecast. Yeah, to illustrate this further, here is basically precipitation, 6-hour accumulated precipitation, I think. And for a 10-day forecast, and we can see the AIFS control member, here the AIFS ensemble control member, and then the AIFS single. And again, what you can see is that here, while AIFS control and AIFS ensemble control have quite a lot of variability, also at the smaller scales, you see this much smoother fields for the AIFS single, which of course are also very skillful forecasts, but they look clearly much less realistic in terms of physical properties. So what is the configuration of the AIFS ensemble? We have 50 perturbed members, because once we have trained the system, even with 2 members, we can generate as many members as required. So we start with 50 perturbed members, which use the initial conditions of the 50 AIFS ensemble members. And we have 1 control member, which starts from the unperturbed initial conditions of the AIFS ensemble. Of the AIFS ensemble control member. The forecast range is 15 days. We have we output data of an N320 grid, so approximately 1/4 of a degree spatial resolution. It has 6 hourly output, like the AIFS single. So one thing to actually look out for is that the AIFS ensemble training is inherently probabilistic, so it always has to reproduce the variability. So the control member of the AIFS ensemble still has this intrinsic stochasticity or this representation of uncertainty. And you can think about it in a similar way to the stochastic representation of model uncertainty in the AIFS ensemble. So what this means is that if you plot the AIFS control scores of the AIFS control, AIFS ensemble control, and for example, the AIFS ensemble control of the physics-based system, then on average, the AIFS on control member will be less skillful. It's still a very skillful forecasting system, but because it still has this inherent uncertainty representation, you can't expect it to perform better in terms of scores currently as the AIFS ensemble control member. Just to watch out for, but I think it's still a very valuable addition. So because then we also plot it in charts, so you can learn more about the statistics of the system, how it behaves, and so on. So now, of course, we are interested in the scores. How does it perform? How does it compare to our AIFS ensemble? And here we have one of our popular scorecards. So blue means better. So the AIFS ensemble performs more skillfully than the AIFS ensemble system. And we can see that there's quite a lot of blue, especially strong for upper air scores, like here at 500. And where you can see quite a bit of red is in the upper part of the atmosphere, and that's similar to the AIFS single model and partly also related to the weight, how much weight we put in the loss on the different levels and at the different part of the atmosphere. But so yeah, that's certainly a degradation here, but a lot of improvements for upper air variables, and indeed also, for example, for quite a few surface variables. So for example, 2 meter temperature, for 10 meter wind, it's a bit more mixed. It looks quite blue against own analysis, against AIFS analysis, but against observations, it's a mixed signal, and then total precipitation tends to be improved in the first half of the forecast and some red in the later half. But yeah, overall, a very strong forecast. You can see these improvements go from up to 25% or more, well, up to 25%. And one thing to also look out for is that we also see increased spread in the early part of the forecast. And that's most likely, that's related to the fact that we use the same initial conditions as for the AIFS ensemble. And there might be some retuning required eventually, but we thought this is the fastest way to an operational system if we reuse what we have already. So to look at some example scores, for example, you can see here Z500, quite a bit of improvement, but the same true for T850 here against observations, and 2 meter temperature. And then in general, in the tropics, there are also large improvements. So it ranges from 12 hours to several days in terms of score differences. So yeah, overall, very skillful system as measured by scorecards. And then if we look at some example variables which are new in the system, for example, we also output total cloud cover here. And I think this nicely demonstrates the different behavior from AIFS single, for example. So in gray, you have the observation, also distribution. So here you can see the population, and here the total cloud cover. And you can see how the observation align. And then you can see in red the AIFS control member, and in blue the AIFS ensemble control member. And you can see that they nicely follow the observations, while AIFS single, because it tends to smooth out things, has a bit of a different distribution. And in fact, this difference becomes more pronounced over time, while the AIFS ensemble maintains its the alignment with the observations, basically statistics. We also have 100 meter wind speed here as an example, and there you can see the thing I mentioned before, that the AIFS ensemble control member is somewhat less skillful than the AIFS control member. Here you see you see some difference here. But then if you look at the ensemble mean forecast, or root mean squared error of the ensemble mean, you can see that after day 2 or day 3, the AIFS ensemble actually has the lowest error. And that's also then reflected in the CRPS of the system. And then we also, as an example here, have solar radiation at the surface. Again, the IFS ensemble, and here in blue, the AIFS ensemble, which shows again quite strong performance in this area. So if you want to look at the systems, you can go to our charts, and we have a selection of plots for the AIFS ensemble here. For example, you can compare spread and ensemble mean plots between the IFS and the AIFS ensemble. And then also for quite a few fields, we plot the control forecast of the IFS ensemble, which again, you can compare then with the IFS control and also the IFS single. And I think it's quite useful to look at it and to get a feeling about how these very new systems behave and what the similarities are, where they have behaved differently from what we had so far, and so on and so forth. So please go and look at the plots. And what we also have, for example, here is probabilities here for precip. I selected some plots here for total precipitation over the last 24 hours. I think this was a 5-day forecast. And for here, larger than 1 millimeter, the probability, you can compare again the IFS ensemble with the AIFS ensemble, and then larger than 5 millimeter. And just to illustrate that these look quite realistic, so in accordance to the scores, what we expect, system produce realistic patterns and forecast maps. And yeah, that's, I think, quite reassuring. And of course, then we also want to look at or show you some case studies, again, just to get an impression how things behave and how things work. And here, that's a case study for a 24-hour precipitation event with intense precipitation in the Italian Alps from the 16th April to the 17th of April. And what we basically look at is this little black box here, which is put around the largest or the most intense precipitation. Here you see the observations, here the IFS ensemble member 1, and here the AIFS ensemble member 1. And just to illustrate how both systems capture this intense precipitation pattern, of course, both underestimate the maximum values, and also to keep in mind that these are, of course, one ensemble member of the 50 members, so each member will have a slightly different pattern, but the overall story is quite similar. So both IFS and AIFS capture basically the overall pattern, and the AIFS ensemble tends to underestimate it a bit more than the IFS ensemble, which probably is related here also to resolution of the two systems. Here we have 9 kilometer resolution, but here we have a quarter of a degree resolution, so it's a lower resolution system, what you can see also at the pattern. Of course, it's important then to look at the statistics for the system, and that's a plot here which shows the precip and shows the forecasts valid at the time, but initialized further and further away from the actual event. So first both systems, and basically, yeah, the IFS ensemble here in blue and the AIFS ensemble in pink or reddish colors here. And then in cyan, the model climatology. So both systems first didn't have this imprint of the event, so some indication of large precipitation values, and then the closer you get, the more they highlighted that there will be indeed a strong precipitation event. And as we could see from the plots before, the AIFS ensemble had somewhat lower values than the IFS ensemble, but still highlighted the intensity of the precipitation. And yeah, and basically the maximum of the model climatology here is indicated by this rectangular figure, the observation or the analysis itself had this green dot here, and then the actual observations were up here. So both systems didn't manage to present the full intensity, but highlighted a strong event compared to their model or to the model climatology of the IFS. Then coming to another example or case study, and that's 2 meter temperature in April. And this was quite high values here. And in here, the observations, here you see France, which showed high values, and then the 24-hour forecast from the AIFS Ensemble clearly underestimated the temperatures, while in this case, the AIFS Ensemble showed quite nicely these these high temperatures here. And again, we show now forecasts for this rectangle, or for this little box here, similar to the precipitation. So again, the closer you get to the event, the better the forecasts become. And here the AIFS Ensemble nicely highlighted these high temperatures, while they were underestimated quite a bit or somewhat by the AIFS Ensemble. So again, I think a nice illustration what to expect from the systems and how they can perform. So a short comparison, what do other probabilistic machine learning models do? Here just one example plot comparing IFS, our IFS Ensemble, our AIFS Ensemble, the new system, and then here, for example, GenCast developed by Google DeepMind. And what we can see is here for 2 meter temperature that GenCast, for example, has lower forecast errors than the IFS in the first half of the forecast, and afterwards they perform similarly. And then you can see that AIFS CRPS has even lower errors. So of course, for other variables, these systems might actually be much closer, but overall, just to illustrate that we really think we have a state-of-the-art system here with AIFS CRPS. So far, so good, but coming now to our known issues. Of course, it's a new system. It's not physics-based. It has its own quirks, and this is something we still are learning about, and we also very much appreciate user feedback. And we have here a web page about known forecast issues. And yeah, if you find something reported, help us to improve the system, and hopefully the next version will be improved. So one thing to look out for is there can be unphysical pressure and temperature values develop in regions with high orography, and often underground, basically, we have an increase of values, which especially happens, or you can see from beyond 10 days or so. So this is something to watch out for. And also then in these regions, there can be artifacts in terms of 2 meter temperature. But yeah, we also had a region in the Red Sea, or the Red Sea being affected. Again, this is expected to happen after 10 days and so on. But yeah, something to look out for, and we are looking into this and trying to improve this now. In general, we have some over dispersion, as I already said. So in the first half of the forecast, the spread tends to be larger than the error for the AIFS Ensemble, and related to the sharing the same initial conditions. The cloud cover statistics look quite nice, as I showed, but when you look at the clouds, they appear to have reduced spatial resolution. So you see some blocky structure here. Again, something we are looking into and hopefully can be improved in the future or soon, but this is still under investigation. And then another thing which happens is that when we look at precipitation, there can be very small values of precip in very arid regions, like desert regions and so on, where there shouldn't be any precip. For example, here you can see forecasts accumulated over 24 hours. And what you can see is you have small precipitation values, while if you compare to the IFS, there are really none in these regions. So again, these are still outstanding issues, which one has to look out for, which has to know about. But overall, hopefully we'll be able to improve upon these soon. And with this, I want to hand over to Maartje to talk about the data part.
Hello, my name is Maartje, and I will talk a bit about the data practicalities. So which data are available, how you can get the test data, the file naming convention, etc. So we created this implementation page. The link is on the slides where everything is explained in detail. So I would really recommend you to have a look. You see here an overview of the control and perturbed forecast product. So the parameters, the level type, which is pressure levels, surface level, and soil level parameters. Almost all the parameters that are available for AIFS single are also there in AIFS Ensemble. We don't only have control and perturbed forecast products, but we also have some post-processed products, so ensemble mean, standard deviations, and probability parameters. Again, an overview can be found on the implementation page. So when you look at the new data, you will see it's produced for all 4 runs. The forecast range is 15 days. If you try to download the data via Mars or install it on the PRED, you'll have to use classes AI, stream is Info, and the model is AIFS ENS, so not AIFS single, which is there for the other data. The resolution is about 31 kilometers. It's on an N320 grid. And we have 50 ensemble members, as also mentioned by Simon. All the data that is produced will be in GRIP2 format. We have step 2 for all parameters. This is to help you. So for the accumulated fields, step 0 will have a value of 0. And for the instantaneous fields, these come from the AIFS analysis and are then regridded to the N320 grid. The data will be available according to the same schedule as the IFS data, which is the same as for the AIFS single data. They follow the same schedule, just to be clear, but they follow the same schedule as the AIFS ensemble data, just to avoid confusion. Pre-scheduled data will also be available, but only for users who have the option to install this, so people with the silver service package or gold. And there's no delay on the open data platform for the AIFS ensemble data. That will be made available as open data. So they will be there as soon as they are produced. So how do you get these data? The test data are now available for dissemination. So people who have access to our PRED, the product requirements editor, can install the data themselves. To help you to install the data, we created a snippet. So we realized some people may be not aware that this exists, but if you go in the PRED, there is this on the right top, there is a symbol with 2 triangular brackets where it says snippets if you click on it, and then if you search for set 10, which is AIFS Ensemble, or you just search for AIFS ENS, then you find an overview of all the subsets that are available. And if you then click add, you get a template of what it should look like, and you can adjust it to your requirements. For people who don't have access, please contact us, data support, open the ticket via support.ecmwf.int, and we will help you to set you up. Also, of course, for all the people who can, in principle, install it themselves but have questions, please don't hesitate to contact us. The file naming convention follows the same as the AIFS and single data. So you have destination, feed, model, class, stream, type, the production date, the valid date, and the steps. So you see here an example for data that is installed in feed TA of destination DSC. You see that at the end here, there is an X0103. That is the version number once the data gets in operation. So from the 1st of July, this part is no longer there. So it's good to be aware of that. You can also already get the data from Mars. Make sure that you use classes AI and the model AIFS ENS. Also, there are test data can be found on the open data. There is this folder AIFS ENS test data. And if you go into that, you can find the date, the run, then you click again on the folder AIFS ENS, and then info, and then you will find the different data that you need. After implementation, it will no longer be in this folder, but it's just following the normal structure as the other data. So you go in the date folder, and then you eventually click on AIFS ENS, and you will find it like that. Then the graphical products. There are 19 new graphical products in OpenCharts from this data set. They are not available before the implementation date. But once they get available, you will see 12 with full members, 1 meteogram, 7 with ensemble mean and spread, and 4 with probabilities. And then there are also 7 from the control. Like for AIFS single, you can also access, run the model yourself using Hugging Face, which is an open platform for sharing the model. There will be also an interactive notebook that explains how to run it from the ECMWF Open data, and you can also then adapt it from other sources. Also, this is not yet available, but will be only made available on the 1st of July, and the license will be CC by 4, so under the open license. And with that, I will hand back to Simon for some final messages.
So what more to expect in the future for the AIFS Ensemble? Basically, we plan to expand the products to offer more products. And here, as Florian said, it's really valuable to get your feedback. What are your highest priorities? Where should we move forward things first? Then, of course, we plan to go to higher horizontal resolution, for example, 9 kilometer, like the AIFS Ensemble system, but also higher temporal resolution. We will look for further forecast skill improvements, and I think there will be nice things coming up soon. And then a big part will also be the greater Earth system representation, like atmospheric composition, waves, ocean, sea ice, hydrology, and so on. In terms of when the next AIFS cycle is planned, so in general, we will target a more frequent release cycle compared to AIFS, but we don't have any fixed release schedule now. When new cycles, we will introduce new cycles when we think we have nice improvements ready. And with that, to summarize, AIFS Ensemble, the AIFS Ensemble will be implemented on the 1st of July. The forecast course show pronounced improvements compared to AIFS. The AIFS Ensemble for many fields, as we showed. There are some known issues, including spatial artifacts, and hopefully we will be able to improve these in future cycles, hopefully soon. And one thing is also that the AIFS Ensemble currently only provides a subset of the products we have in the AIFS. So many of the same products as AIFS single, but also, this will be expanded in the future. And then I think a nice thing with AIFS is that it's very quick, so we can release it earlier, so up to 1 hour compared to AIFS. And with that, I thank you for your for listening. And if you have any questions, let us know. Thank you.